For centuries, we've wondered how the universe came to be. Our next guest says that if a recent theory is confirmed, quote, it will have increased our empirical window on the origins of the universe by a margin comparable to the amount it has grown in all of the rest of human history. Wow, let's find out why. Joining us now for more on our expanding knowledge of the cosmos, in Phoenix, Arizona, we welcome back Lawrence Krauss, theoretical physicist and the director of the Origins Project at Arizona State University. And Lawrence Krauss, great to have you on TVO again. How's things going?
It's great to be back. It's a little warm here right now. I'd probably be happy to be up there right now. I assume the snow's over.
Yeah, but just barely, actually. Okay. Anyway, I want to start with this, and I think in your answering the question, you might want to give us a bit of a checklist as to what makes this moment in our understanding of what we're talking about tonight such a tipping point, because we seem to be hot on the heels of some unprecedented discoveries. Over to you, sir.
Yeah, it's been a very exciting last couple of years because at the two extremes of scale, at the smallest scales we can measure and the largest scales we can measure, we have now, in some sense, hit the Holy Grail. Just a few months ago, the announcement was made of observations that really turn metaphysics into physics, that take us back literally to a millionth of a trillionth of a trillionth of a trillionth of a second after the Big Bang, which is a time frame I never thought we'd be able to observe directly. And if they hold up, and I should say that it's just a single observation right now, and in science we have to be quite skeptical. It has to be confirmed before we can really rely on it, but will allow us to test theories about the beginning of our universe and potentially the existence of other universes, and even the possible existence of grand unified theories that might unify all the forces in nature. At the same time, we have finally, after half a century of searching, discovered the Higgs particle, which may not sound like much, it's just an extra particle, but it's really the capstone of the greatest intellectual enterprise that humans have ever taken, the fundamental standard model that really describes everything in the universe we can see on a fundamental scale, and also points us, we hope, in a new direction towards understanding really why we're here.
Do you think we are at this moment in our understanding of the origins of the universe? I guess I'm wondering what gets more credit, the fact that our scientists may be smarter than ever, or the fact that our technology is better than ever?
Look, physics and science is an empirical discipline. Never forget that. I'm a theorist, and I'm the first person to point it out. We depend on what we can see, and what's been exciting is that we're opening up new windows on the universe. And every time we open a new window on the universe, we're surprised. So we are driven by experimental data, and that's the way it should be. And it's that we've been waiting for. If you locked a bunch of theorists in a room for a bunch of years and asked them to come up with a picture of the universe, the picture they'd come up with is completely wrong. Because as I like to say, the imagination of the universe far exceeds our own imagination. Mm-hmm. And we are lucky to have new technologies, new windows for, in the one case, looking at what are called gravitational waves from the Big Bang, and in the other, finally, to put together an accelerator that we tried to build 40 years ago, but in this country didn't have the courage to do. Literally the most complicated machine humans have ever built, as I like to call it, the Gothic cathedral of the 21st century. We put those extremes of technology, looked at the universe, and that's what's driving our knowledge, not that we're any smarter.
Okay, let's start to unpack some of the things that you advanced in that first answer, and we're going to start simple here. Let's start with, and I don't mean the TV show here, I mean the real thing, the Big Bang Theory. When scientists refer to that, what do they mean?
Well, we refer to the fact that our current universe is expanding, and we've known that now for 80 some odd years already. It's expanding, and therefore if you work backwards, our observable universe was once smaller and smaller and smaller, and if you go back in time, eventually, if you take the equations at face value, it takes us back to our entire observable universe occupying a single infinitely dense point at the beginning of time. Now, we don't believe that extrapolation goes back to t equals 0. But what is important to realize is that this idea is not just a theory or in the colloquial sense. It makes predictions from an early universe, a hot early universe, of what happened in the first second of the universe that have been verified over and over and over again. The Big Bang really happened. And what we're trying to do is push back to closer and closer to t equals 0. Up to this point, we were able to go back to maybe a millionth of a second after the Big Bang. With the observations at the Large Hadron Collider, which we may talk about, it takes us back to a millionth of a second after the Big Bang. And as I say, the most recent observations push us back to almost t equals 0. But the Big Bang is just an expansion of our universe. Everything we see was once contained in a region smaller than the size of an atom. It's hard to imagine, but it's true. In fact, I wrote a whole book about it.
Yeah, and we talked about it on this program, I believe.
Yeah.
Okay, so take us back to that moment. This is almost 14 billion years ago, is that right?
So about 13.8 billion years ago, give or take a few.
Give or take a few. Okay, now let's go a little more recently. 50 years ago, two scientists detected something called the cosmic microwave background radiation. What's that?
It's wonderful, by the way. They detected it by accident without even knowing what they were looking for, which is just wonderful. They didn't know what the heck they were doing, but they won a Nobel Prize anyway. Because you don't have to know what you're doing to win a Nobel Prize. You just have to do it. But what they were doing actually was trying to do radio astronomy, and they took an existing antenna and turned it up towards the sky. And what they got was disappointing to them: noise. They couldn't get rid of the noise. They even cleaned, as if you read their paper, a white dielectric material from inside the antenna, which was pigeon droppings. They still had the noise, and they were very disappointed until they went down the road to Princeton University to a bunch of physicists who were even more disappointed because they'd been building an antenna to look for that noise. What that noise was the afterglow of the Big Bang. Radiation coming at us from early in the history of the universe, not the earliest moments, because if we look out, if the universe is 13.8 billion years old, you'd think if you look out far enough, you look back in time and see the Big Bang. In principle, that's possible, but between us and the Big Bang, there's kind of a wall, because the universe was getting hotter and hotter and hotter as we go back in time. And when the universe was about 300,000 years old, it was 3,000 degrees in temperature. That's hot enough that neutral matter couldn't exist anymore, and you had a dense plasma of material, and you can't see through that plasma. Literally with light, if you tried to look past it, you can't see it. Like I can't see past the walls in this room. But playing it forward, as the universe cooled, matter became neutral, it became transparent, and you'd predict if there was a Big Bang to see radiation coming from that surface where the universe became neutral, coming at us in all directions. It was once 3,000 degrees. It's cooled in the interim. It's about 3 degrees now, and that was the radiation that was discovered in 1965 in New Jersey, of all places. And taking images of that radiation give us a picture of what the universe looked like when it was only 300,000 years old. That was our earliest baby picture of the universe, if you want. And that picture also got a Nobel Prize because, after all, it showed us what the early universe was like even before stars and galaxies were created. And that cosmic microwave background radiation has been probably the best and most important observable in cosmology, because it has allowed us to turn what was considered by many scientists to be more of an art than a science into a precision science. You can measure things to 4 decimal places and suddenly test properties of the Big Bang that you never could earlier.
And was one of the insights in that you scientists, you can't just look for things, you also have to listen for things. Was that part of it?
Well, I mean, you have to use everything you can to try and learn about the universe. And listening in a broad sense is true. We're looking at that early time. There was this dense coupled system of matter and radiation. And as matter tried to collapse due to gravity, it was pushed apart by radiation. And you got these kind of oscillations called acoustic oscillations. And so it sounds like sound. It's not really sound. But those kind of oscillations in matter and radiation allow us to test ideas about the geometry of the universe and ultimately the origin of all structure. And now, the very colossally intense processes at the beginning of time that literally produced waves called gravitational waves, which stretch and shrink space itself.
Okay, let's introduce another term now related to what we're talking about that people may understand from an economics point of view but may not understand from a scientific point of view. You know where I'm going. What's cosmic inflation?
That's right. Inflation, as one of our economic gurus here once said, periods of inflation are inevitable. And it's true not just for on Earth, but in fact in the universe. Inflation is an idea which was first proposed in about 1980 by Alan Guth. And it was an idea to explain what otherwise seems some incomprehensible aspects of our universe. Our universe is relatively smooth on large scales, but it shouldn't be smooth because over there could never have communicated to over there until today. So how would they know to have the same temperature? Well, Alan realized that extrapolating ideas from particle physics by a huge amount, and by a huge amount I mean by 15 orders of magnitude in scale, you could naturally predict that in the earliest moments of the Big Bang, again, a millionth of a trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe would get stuck in some state where energy would be stored. An immense amount of energy could be stored in empty space, causing the expansion of the universe to blow up and inflate, that's where the word comes from, by a huge amount, over 90 orders of magnitude in volume in a time period of a millionth of a trillionth of a trillionth of a second. It's amazing. But what that would do, not only was it natural and based on the ideas of particle physics, but would explain the properties of the universe we see, which couldn't be explained otherwise. In particular, if our observable universe was once much smaller before inflation, then light could have communicated at very early times across what is now our whole observable universe, making it uniform at the same temperature. Then it blew up rapidly and formed the universe we see, and even better, there were amazing ideas that quantum effects during that period of blowing up would produce fluctuations in density which could produce all of the observed structures we see in the universe today. And when we looked at the microwave background, when we imaged it over the last 20 years, the image we see is essentially precisely the kind of image you would have predicted if inflation had happened. So we had suggestive evidence that inflation really happened at that time, but it's hard to probe directly just using these density fluctuations because of all the stuff happening when the universe was 300,000 years old. To go back earlier, you had to find a new probe, and that's what we found.
Well, I appreciate it, and I've been reading your stuff, which suggests that you are not quite ready to pop the champagne cork on this one yet. However, and I suspect you've seen this video out of Stanford University, the Stanford physicist Andre Linde, whose theory this is in the first place, did have a surprise visitor knock on his door with a bottle of champagne because they did some independent research on this and found that the theory worked. We're going to show that video, and then we'll come back and chat. Roll tape, please.
So today I'm going to tell him our experiment, BICEP 2, based at South Pole, has found the smoking gun evidence of inflation. He has no idea that I'm coming.
Oh, wow.
So I have a surprise for you.
Wow.
It's 5 sigma at 0.2.
Discovery.
Yes.
What? Just a second. Can you repeat it?
5 sigma, as clear as day, are at 0.2.
Can you repeat it again?
Are 0.2 plus minus
0.2.
0.05.
We don't expect anybody. Renata tells it's probably some kind of delivery. Did you order anything? Yeah, I ordered it 30 years ago. Finally, it arrived.
Cheers, cheers.
Congratulations. Oh my God, I'm going to break something.
Okay, so that's the moment where somebody brings additional evidence to him that his theory, which he helped work on, makes sense and holds up. And I want to put the quote, I mentioned this quote off the top of the program, of yours. I want to put it back to you and have you explain why you think, if the discovery holds up, it will have increased our empirical window on the origins of the universe by a margin comparable to the amount it has grown in all of the rest of human history. How so, Lawrence?
Well, because as I said earlier, before this, our best direct evidence of what happened in the early universe was looking at this cosmic microwave background, which took us back to 300,000 years after the Big Bang. The signal that these people, which we still haven't discussed, which I'm sure we will, that these people have detected, and it was a little dramatized, I must admit, in that video clip you showed, but that signal, due to these things called gravitational waves, if we're right, and all the evidence suggests we are, points back to a process that happened during this very earliest moment of inflation. It's an unambiguous prediction of inflation that these things called gravitational waves will be observed. All the other things can be played around with, but not that. And if that's the case, these waves interact so weakly that they've really been propagating to us from a millionth of a trillionth of a trillionth of a second after the Big Bang. And that means that we've changed everything. We've changed by so many orders of magnitude, over 40 orders of magnitude in scale. 40 orders of magnitude in scale. That's a 1 with 40 zeros. The time period we can go back and understand the history of the universe.
I think we're actually looking at a picture right now of these gravitational waves that you're talking about. Would you compare them, if you were going to use an analogy, to say like a telegram sent from the beginning of time?
A telegram sent from the beginning of time is a pretty good analogy, in fact. It's one that's been waiting for us to open up. It's been hiding there. It's like one that was under the rug that you finally found. And what's really neat is that this telegram made it through storms and rain and sleet and stuff that nothing else could get through. That's what's wonderful about gravitational waves. Most people don't realize that gravity is the weakest force in nature. You know, when you get out of bed in the morning, it certainly doesn't feel like that. But in fact, it is. Gravity is far weaker than the other forces. And these gravitational waves, and I know we'll want to spend a little time talking about exactly what they are, but they interact so weakly that they could make it through that hot, dense universe to us today. And they, in principle, as they sort of said in that video, or the smoking gun of inflation, we've been, for a long time, I actually kind of predicted this signal almost 30 years ago myself after inflation came out, that if inflation happened at a high enough scale, we might see it in the cosmic microwave background. But like many people, you know, you kind of figure it's not actually going to happen. But it is, while many other things can be changed as you change the theory, this is the clearest possible evidence that will allow us to test these otherwise very speculative ideas. Because inflation, even though it was well motivated, is based on physics we've never measured. Physics at what we call the grand unified scale. And without an empirical handle, it's all just talk. And so what's exciting is that now it's more than just talk.
Well, more than just talk, and in fact, the guy who made the discovery at the South Pole where they were doing this investigating, is it John Kovac, I think is how he pronounces his name?
John Kovacs, yeah.
John Kovac. He said that the chances that these results were a fluke are 1 in 10 million, meaning obviously he believes it's the real deal. Do you?
Well, you know, you have to be careful. And they've done a very careful work. They contacted me before the result came out to talk to me about it. And they know that this is a big deal, and they don't want to be fools in front of the world. So they've been looking at this for 3 years, trying to make sure that they didn't screw up. But, you know, it's a hard business. And they can say that there's a statistical chance of 1 in 10 million that this is wrong. But that's not what drives what is the case, because there's also other effects that you can't control. So they can look for all sorts of things they can control, and they can say that this is a real signal they're seeing. So what they can say is definitively, this is a real signal they're seeing. But to make the interpretation that this real signal comes from inflation, you have to make sure there aren't other what we call systematic effects. And people have suggested possibilities. And so what we really need to do is, in spite of the fact that this signal, it sort of looks like inflation, it walks like inflation, it quacks like inflation, it's probably inflation. The fact is that until we can test it with another detector, this could just be a very bad accident, not just at the 1 in 10 million level. For example, they look at a very small section of the sky. There are other processes that could have happened in that very small section of the sky, which just would have been a bad luck for them, nearby processes that might, and I repeat the word might here, that might mimic their signal. Right now, what's great about this observation, however, is it's almost like the earlier observation of the cosmic microwave background. Once we know that signal is there are a host of experiments at the South Pole and other places around the world, and in particular a satellite called the Planck satellite, which is working right now and going to report data in September, that can check this result. So it's not as if we have to wait around in suspense. Once we know it, it's a lot easier to look for something once you know it's there. Mm-hmm. When you don't know if anything's there, it's a lot harder to rule out noise and other backgrounds. But once one set of people have claimed a signal, it's a lot easier for other experimentalists to look for that signal and either verify it or demonstrate that it's wrong. So we'll know by the fall whether this is right. And as I say, it looks very good, and I'm optimistic, but one has to be skeptical. And it's very important not to overstate the case until it's very important in science to be skeptical. In fact, as Richard Feynman said, the easiest person to fool is yourself. So you have to always second guess yourself.
Let me read this. This is from a few months ago in the New York Times, a short excerpt for you, and then I'll get you to comment on this. The Times writes, confirming inflation would mean that the universe we see, extending 14 billion light years in space with its hundreds of billions of galaxies, is only an infinitesimal patch in a larger cosmos whose extent, architecture, and fate are unknowable. Moreover, beyond our own universe, there might be an endless number of other universes bubbling into frothy eternity like a pot of pasta, water boiling over. Explain what that's about.
Well, it's a wonderful analogy from Dennis Overby at the Times. And the idea is that inflation is almost too good. Inflation causes the universe to puff up. But it actually doesn't in most theories. In fact, this is what Andre Linde added to Alan Guth's work, is that it tends to not ever stop. The universe what was the universe, and by universe I meant everything you could once have seen or everything you could ever seen, but that region of space that starts expanding essentially never stops and continues to expand faster and faster and become larger and larger. And what happens is small pockets fall out of inflation. There's what's called a phase transition, like water melting or water freezing. In certain small regions, certain regions leave inflation, and you get what is essentially a hot Big Bang. And our observable universe was one such region. But what that means is that if this is really due to inflation, it strongly provides evidence for something which again sounded like metaphysics, and I've written about it in The Universe from Nothing and others, that our universe is just one pocket in this metaverse or multiverse, that most of which has continued to expand faster and faster, and out of which there may be other universes, if you wish, being born at every instant and other universes dying. It means that this process could go on forever, and our universe is just a small random accident in a vast multiverse, and it's fascinating because it means as each universe sort of pops out, falls out of inflation, it can fall out in a different way. It's like falling down a mountain. You can fall in lots of different directions. And each different direction that you leave inflation, in some sense, could give different laws of physics in that region of space, or at least certain different laws of physics. And if that's the case, it may be that many of the fundamental laws that we see and think are truly fundamental are just accidents of our experience. It could be in each universe there are different laws of physics, and that may help explain other paradoxes about the universe we see. So if we can really demonstrate that inflation happened, it gives us incredibly strong indirect evidence of the existence of other universes, which we'll never see directly, but it takes it out of the realm of metaphysics. It's like the fact at the turn of the last century, in the 1900s, no one could see atoms directly, but all of the indirect evidence told us atoms exist. Now we may be in a situation where we'll never see those other universes directly, but we can have great confidence if we can test these ideas more and more that they exist. And that changes our picture once more in the sense that I referred to earlier, not only in this very small, but in the very large. It says the universe on very, very large scales is very different because it's not a universe, it's a multiverse full of regions that are just being born today, other regions that are dying. And that's very different than the picture we had 30 years ago.
You've been at, excuse me, you've been at this so long that does this still blow your mind like it probably does our viewers right now?
Yeah, more, maybe more, because you know when you're sitting and you're a theoretical physicist and you speculate about what might be, there's nothing more terrifying or perhaps less plausible than the possibility that the universe might actually obey what you're saying. In my career, most of the time, the universe isn't smart enough to do what I say it should. But so it's really remarkable when these very speculative ideas that seem well motivated, but almost seem too good to be true, actually work out. I think in some sense I'm more amazed than someone learning about it the first time, because it is remarkable that the human mind in advance in some sense can anticipate things well enough to actually understand the evolution of our whole universe. It is amazing.
Okay, in your first answer some minutes ago, you talked about the Higgs-Boson and about this particle that was just discovered not all that long ago. And I know in your work you have compared the Higgs field to molasses. And again, since we're dealing with analogies here that help explain these things, perhaps you can help us understand now why the Higgs field is like molasses.
Well, you know, when you discover a new particle, people's first response may be big deal, there are lots of particles. The Higgs particle is special because it's associated with an idea which, once again, I thought was too good to be true. I was sure it wasn't true because it just seemed too easy. But the bottom line is that to understand two of the fundamental forces in nature, electromagnetism and the so-called weak force, they have very different properties. One could develop a theory that described both of them, but it gave nonsense unless at some level fundamental particles didn't have mass. The ones we measure now have mass. Now, how could that be? Well, it could be that it's an accident of nature. If you imagine that there's a field everywhere throughout space, an invisible field that permeates all of space, as particles move through it, some particles don't interact with the field at all and they zip through at the speed of light, like photons. But other particles interact with that field, and it's like swimming through molasses. If you're swimming through water, you can swim pretty fast. If you try and swim through molasses, you feel a lot heavier. And what the idea was that certain particles interact with that background field more strongly and act as if they're heavy. If the field wasn't there, they'd be moving at the speed of light and be massless like everything else. So the fact that we measure particles as having mass, which is so essential to our own existence, is really an accident of nature, an accident of this background invisible field. Now, in physics, of course, it's not like religion. In physics, postulating a background invisible field isn't good enough. If you can't measure it, it just doesn't fly. And what's neat about postulating an invisible field, in this case, is in physics, every field is associated with a particle. And the laws of quantum mechanics say if there's an invisible field and you spank empty space hard enough in a single point, from that field you'll kick out particles. And we had predicted that these particles, called the Higgs particles, should exist if the Higgs fields exist. And that's what we've been looking for 50 years. And we tried to build an accelerator in the United States, and the Congress, in their wisdom or lack thereof, canceled the project. And the Large Hadron Collider in Geneva was designed in principle to look for it, although it wasn't certain it could see it. And in fact, I was amazed. I expected it would be the last thing it would see. But what it discovered was precisely the kind of particles that we would expect to see if there is a background field permeating all of space. And so we discovered this invisible universe, if you wish, and we've discovered the final capstone of the standard model of particle physics that really explains everything we can see, except it doesn't. Physics isn't over, because although the Higgs field had to be there for this to work, and it's amazing that it is, we don't understand why it formed the way it did. Why did this field form in the early universe? What governed the physics of that? That's what we're trying to understand at the Large Hadron Collider. And what's amazing, of course, is that with our new observations in cosmology, we can come at it from a different way. My colleague Sheldon Glashow was a Nobel Prize-winning physicist, used the term Ouroboros. I don't know if you know what Ouroboros is. Do you know?
No.
It's an ancient Sanskrit and then Egyptian symbol of a snake eating its own tail.
Oh, okay.
Okay? And in physics, that's what's happening. Because of the Big Bang, the largest structures we now see were once located in a distance scale corresponding to the smallest structures we can measure. And so, therefore, at some level, if we want to learn about fundamental microphysics, we can do it by probing it directly, or we can look at the remnants of the Big Bang, where that microphysics got turned into the largest scales we can see. So we can probe the fundamental structure and the fundamental forces from both directions. We're doing it at the Large Hadron Collider, and we have this incredible lever arm now with the cosmic microwave background, because if you take the energy of the Large Hadron Collider, which I repeat is the most complicated, most amazing machine humans have ever built, that energy is only 1/1,000,000th of a billionth of the energy associated with the processes of inflation. And therefore, in some sense, the universe is allowing us to measure fundamental physics on a scale we'll never build an accelerator big enough on Earth to measure.
Okay, let's finish up on this. I'm going to quote you to you. This is from your
I like that.
2012 book, A Universe from Nothing. Here's the quote. Our discoveries in fundamental physics and astronomy over the past 40 years have changed our understanding of our place in the universe in profound ways by changing not only the questions we ask, but the very meaning of the questions we have asked. That, as I want to stress once again, is perhaps the greatest legacy of modern science, a legacy it shares with great music, great literature, and great art, and one that needs to be shared more widely. Let's finish up on just having you elaborate on the point that you're making right there.
Well, I think, first of all, because science produces technology, we often say, if it doesn't produce new technology, if it doesn't produce a better car or a better toaster, what's it good for? And the point is that science really does what art, music, and literature do as well. They change our perspective of our place in the cosmos. And the scientific enterprise does just that by forcing us to be a little uncomfortable. Sometimes when we look at a painting, it may jar us, or we may hear music that jar us, or a story that upsets us in some way. But the inevitable end of that is forcing us out of our local myopia to view ourselves in a different way. And what science is doing is, with these new discoveries, forcing us to realize that what we once thought was true is not only not true, but even the very concepts are myopic. We evolved on the savannah in Africa to evade lines, not to understand quantum mechanics, not to expect that our universe is just some random, insignificant universe in a multiverse of space and time. And those ideas, and for many people, are jarring and unsettling because they want to feel special. And for me, it makes me feel more special to know, in some sense, that I'm cosmically insignificant. because it means the meaning I make in my own life is the meaning I create. We are fortunate enough to be here, you and I talking at this random moment, 13.8 billion years after the Big Bang, in this random place in the middle of nowhere in the universe. But our minds have evolved through evolution to allow us to comprehend these amazing things. We should make the most of our brief moment in the sun and enjoy being surprised every day.
Well, I know that I love this job because I get to come into work every day and learn something new, and you never, as we say in Canada, fail to put the puck in the net when it comes to that. So Lawrence Krauss, it's awfully good of you to join us on the line from Phoenix, Arizona. Come back and see us again soon, and thanks so much for your time.
Anytime. I love your program. I love talking to you.
Thanks so much.
Support Ontario's public television. Donate at tvo.org.